Hi everyone, today I'll be talking to you guys about Huffman Encoding. What is Huffman Encoding, what are its strengths and limitations, and how is it done exactly? Well, Huffman Encoding is a lossless data compression algorithm. Let's explain what it does by showing a few examples. So let's say you have 4 characters, A, B, C, and D. Well, you can represent them with 2 bits each, and these would be their codes. And the average number of bits used is 2 bits. Huffman Encoding not only considers the characters, but it considers how frequent a character is within a message. So let's say this is our message, A, B, B, C, and D. Well, A obviously appears in half of the message, so it has the frequency of half. B occurs in a quarter of the message, it has a frequency of a quarter, and so on. So Huffman Encoding takes the characters with a larger frequency and assigns them a shorter length, and characters with a smaller frequency like D and C in this example with a longer length. The reason why is when you compute the average length, which takes the probabilities of each character and multiplies it by the length and sums them up, you get an average length, so an average bit usage, that's less than 2, which is less than this. Huffman Encoding also has another strength, which is it makes sure that their codes are not ambiguous. Let's look at this example. A is 0, 0, B is 0, 1, C is 0, and D is 1. Well, this is kind of hard to decipher because C, the code for C, is a prefix for A and B, and that's not very good. So Huffman Encoding completely avoids this, so let's delete that. So those are definitely some of the strengths of Huffman Encoding. What are its limitations? Well, the biggest limitation of Huffman Encoding is that you have to know the frequency of the characters. So to best explain Huffman Encoding, let's go through an example. Let's say you have 6 characters, A, B, C, D, E, and F. And let's say their associated frequencies are 0.4, 0.2, 0.25, 0.05, 0.06, and 0.04. What that means is if you have a text file with 100 characters, then 40 of the 100 characters are A, 20 are B, 25 are C, 5 are D, 6 are E, and 4 are F. Those are their frequencies, so how often they appear out of the 100 characters. So there are 2 steps to Huffman Encoding, and the first step is creating the Huffman tree. So let's scroll down here, and as you can see, I created a leaf node for every character. So there's 6 characters and there's 6 leaf nodes. And I sorted their frequencies from highest to lowest. So 0.4 is the highest and 0.04 is the lowest. So to create the tree, what you do is you take the 2 lowest frequencies, so in this case it's D and F, and you create another node with their sum, which in this case is 0.09. And this new node, 0.09, holds these 2 smaller nodes. And then with these 4 nodes here and this brand new node, you pick the 2 lowest values. So in this case it's E with 0.06 and this new node 0.09, and you sum their values. And you just keep doing this, and over here it would be 0.35, and over here would be 0.6, and over here finally would be 1. So if this root node consists of 1, then that's a pretty good indication that all your probabilities and additions are correct. Now, the second step to Huffman Encoding is going through the tree and assigning values or codes. So you start with the root node, which is 1, and anything to the left of the node you're assessing will be given a value of 0, and anything to the right will be given a value of 1. So in this case, it would be something like this, and 1 here. And then if you're assessing this node, it would be 0 here, and 1 here. And then for this node, it's 0 here. Let's move this up a bit, and 1 here. And then 0 here, and 1 here, 0 here, and 1 here. Now, we created the tree, but how do we assign the values? So, starting from the root node, you follow the path it takes to get to each individual leaf node. So for A, the path it takes is just 0, right? So that's its Huffman code. And then for B, it takes 1, 1, 0. And for C, it takes 1, 0. So just down there and there. And then for D, it takes 1, 1, 1, 1, 0. For E, it takes 1, 1, 1, 0. And then finally for F, it takes 1, 1, 1, 1, 1. So these are the unique Huffman codes. And these make sense because anything with a higher frequency, you want a lower bit representation. And anything with a lower frequency, you want a higher bit representation so that data compression can actually occur. Next, I want to show what I created for my project, which was a Huffman encoder, and I wrote the program in Java. So let's run the program so we can demonstrate what it does. First, it asks me how many sequences I want to compress today. So let's say I feel like compressing 2. Enter the different characters one at a time. So that's A, B, C, D, E, F. And now, please provide the associated frequencies of each character separated by a comma. So 0.4, 0.2, 0.25, 0.05, 0.06, and 0.04. That should be right. And then what it does is it creates the Huffman tree here, and then it also gives the Huffman codes. So if we go back to our codes that we generated here, you'll see that these match these. And what my program also does is it computes the theoretical number of bits it would take to store these 6 characters. And that makes sense because 2 to the power 2 is 4, and 2 to the power 3 is 8, and we have 6 characters, which, you know, it's too much for 2 bits. Now, my program also calculates the entropy value, which is the average information. And finally, what my program does is it prompts you to write out the binary representations in the order we wrote the characters, so A, B, C, D, E, F. And I'm going to do that. And then it calculates the average length, and it compares the average length to the entropy value. So as you can see, compared to 3 bits, which is the theoretical value, we were able to achieve 2.19 for our average length. So that's what my program does, guys. Thank you for watching my video. I hope you guys learned something about Huffman coding.